Hello, class. This is Mr. Hart, and in this podcast, we want to talk about graphing. Now, this is one of those skills that we're going to be using throughout the entire year, so we want to make sure we have a foundation of what it is, what it looks like, the proper way of labeling graphs, etc., because again, we're using this throughout the entire year, so we want to make sure we have a good foundation. Also, I'm going to be including some slides from my good friend Todd Maurer, who's a biology teacher, and he has some great ways of explaining how to make graphs, so I'm going to be using those slides with his permission. Now, to get started, let's talk about a man named Charles David Keeling. Now, you may or may not know this man, but he is famous for a very important graph in science, what is known as the Keeling Curve. And what it was a huge amount of data collected at an observatory that measured the amount of CO2 in the air over time. Now, when you put all this data together in a graph, you get this curve, which is known as the Keeling curve, and it shows that over time, the level of carbon dioxide in the air is increasing, and even though it has some cycling in it from year to year, the overall trend is that it is going up. And this was one of the first arguments for global warming because of the greenhouse effect that was increasing from these high levels of carbon dioxide in the air. And so Keeling won the Medal of Science in 2002 for his work in this. And again, it's been a very influential part of the global warming community's information. Again, we're not going to talk about global warming in this class per se, but what I want you to understand is the importance of having data being visualized. This wouldn't have made any sense really, or at least wouldn't have had the same amount of impact if it was just a bunch of numbers like we saw before. The visualization with the graph is important to see what is going on and to convince people of what is going on. So again, we want to be able to do this in physics so that we can see trends that occur, be able to predict things that are going to occur based on the graph, etc. So, how do we make a good graph, and what does it look like? Well, first of all, we're going to be primarily focusing on the line graph. And the line graph is just a way of showing a cause and effect relationship. We have a bunch of data points, we connect them with a line or with a best fit line or curve, and we can show that a relationship is connecting these two variables. In general, we like to make the graph with the independent variable on the x-axis and the dependent variable on the y-axis, meaning the thing we are changing is on the x-axis and the thing that we are measuring is on the y-axis. So in this graph below, for example, we might be changing the amount of energy we're giving to a system, and then we're recording the resulting temperature in the system. And thus we have the cause, our changing energy, and the effect, the resulting temperature. Now, conventions are important with graphs to make sure that they look nice, they're easy to read. So this is what I want you to include in every graph in this class. First of all, I want you to include a descriptive title describing what the experiment actually was, not just this lab, but some other description that gives an idea of what we're measuring. A labeled X and Y axis with the associated units also included. That's going to be very important. We'll see what that looks like in a second. Also, I want you to include axiomarks equally spaced, so we have a nice linear grid, not just an arbitrary labeling. Then also the data on the graph, of course, that's pretty important for the graph itself. And then last of all, I always want you to draw a best fit line or curve, whatever fits the data so we can see the trend that is going on. So let's see what this looks like. So let's say we're gathering some data on ice cream sales in a given month based on the average temperature. And we want to graph this on a graph. And first of all, we need to figure out, okay, what thing is changing and what thing are we measuring? Well, the thing that is changing is the average temperature, and the thing we are measuring is ice cream sales. So we would put ice cream sales on the left side. We'd put the average temperature on the x-axis, and this is our graphing labels and axes. Then we'd also need to figure out a good title. And so here's a good descriptive title. This would be the correlation of ice cream sales and the average high temperature in Orem in a given year, whatever it may be. And then next we make our grid. We plot all our data. That's a Todd Maurer effect right there for you. Then once we have all the data in place, then we make our best fit line. Now for my class, you just need to be able to visually draw the best fit line. It doesn't have to be exact. You don't have to put in your calculator and do the regression and all that stuff. Just give me a visualization of the best fit line or curve. Okay, so not too bad. Let's look at one other experiment. And again, Mr. Maurer was a biology teacher, so he has a biology example. But let's look at it. It's a pretty good one. So we have plants that were given varying amounts of fertilizer, and the amount they grew after 1 month was measured. So my question for you is, what is the independent variable and what is the dependent variable? Okay, so if we analyze this and we think about it, the thing that was changing was not the amount that the plant grew. I mean, that is changing, but that's the thing we're going to measure in the end. So what really was changing and what we were controlling was the amount of fertilizer given. So that's our independent variable. And then we're measuring the amount of growth, which is the dependent variable. Okay? So let's make this graph. On this left side here, we have all the data for the fertilizer given and the plant growth. So again, the first thing we're going to do is label the axes. Now we don't need to start at 0 unless it's in our data set. And we want to make our graph relatively large. When we're graphing by hand, we want to make it at least a half a page. So we put a title, okay, the effect of fertilizer amount on plant growth. And then we label our axes with the plant growth as the dependent variable and the fertilizer as the independent variable. Again, we want to make sure we have those units marked off, the grams for fertilizer and the centimeters for plant growth. Then what we need to do is determine our axes marks. Now, we need to make sure these are equally spaced and that we can cover our entire range. So what we'll do is we'll first of all figure out how many squares we can work with. This will be dependent on the paper you're using, but in this example I have 21 squares to work with. And then I need to figure out my range for the amount of fertilizer given. And so the smallest value on the fertilizer data point is, I believe, 2. And the largest is 12. So if we look at this, that means we have a 10-gram range for the amount of fertilizer given. Now, if we have 21 squares to work with, we can do a calculation of dividing the number of grams, the range, by the number of squares we have to work with. But when we do that, we get a kind of a weird decimal, 0.47 grams per square. But that gives you an idea of what you should be using as your axes. Don't use 0.47. But we probably should use about 0.5 because that's an easy number to work with. So every other squared gets labeled with 1. Okay? You don't have to do that division, but it may help you figure out exactly what numbers you should be looking at. Okay, then we do the same thing for the plant growth. Again, we have 15 squares to work with, and we have an 80 centimeter range. When we do that division again, we get about 5.33 centimeters per square. Again, that's a really weird decimal, don't use that. But we need at least 5.33 centimeters per square. It might be tempting to go down to 5, but it actually won't work. You won't be able to fit everything. So let's just make it easier on ourselves and make each one 10. Okay, so there we go. Here's our labeling of the axes. Then from there, we just start getting data points plotted on the graph. Hopefully you know how to do that from math class. It's just a simple X, Y location. If you need any help with that, though, let me know. I'm happy to help with that. And once we plot all the data, we draw our line of best fit. And there we go. There is our nice graph with all the conventions in place. Easy to visualize, easy to see what is going on based on the information. So the next thing I want you to do is to take a look at this graph and figure out what is wrong. There's about 5 things wrong with this graph. Okay, so take a second, pause the video if needed. See if you can figure out what 5 things are wrong with the graph on this slide. All right, so hopefully the first thing you saw is that the title is not very descriptive. Again, you don't really know what is going on per se, but you would want to have a more descriptive title than this to make sure everyone knows exactly what you were measuring and what you were doing. Other things that are wrong is that the plant height and the amount of fertilizer given are switched. What we control should be on the x-axis, and what we observe should be on the y-axis. Okay, so we need to flip those. Other things include the fact that we don't have any units with the fertilizer amount on the left side. Also, the spacing of the numbers on the bottom is not linear, right? They're not equally spaced. And then my favorite of all, on the left side, there's just a single number. What does that mean? What is it in reference to? I've seen that before on labs. Make sure you actually have spacing for all of the tick marks on your graph. Okay? But there we go. So that is how we do some very strong, conventional, good-looking, and easy to see, easy to read graphs. Now what I want to do is take a look at what this looks like specifically in physics. There's going to be some slight differences of what we do for our physics experiments. And first of all, I want to take a look at what types of things can be variables in physics experiments. First of all, the big one is time. Okay? Time is going to be something we measure a lot in physics because it helps us determine things like trajectories and motions and forces and momentum and things like that. A lot of these things are dependent on time. And if time's ever included as one of our variables specifically, it is always the independent variable. Okay? Because even though we're often measuring the time that has passed, it is the thing that is causing other things to occur. So it's always the independent variable. It's always controlling the results of the experiment. Okay? So time is always independent if we see it. Other things we'll measure often are position, speed, force, temperature, etc. Also, strangely enough, those will often be the things that are dependent variables: position, speed, force, energy, temperature. So I guess the moral of the story is it really depends on the experiment. So we really need to have a good idea of what we're controlling and what we're measuring as a result, because these things are so interconnected in physics that they are pretty much interchangeable. But again, if you ever see time, it's always the independent variable. All right, another thing I want you to be really focused on when you look at these graphs in physics is I want you to be able to determine the type of relationship that you're seeing in the graph. If you're ever seeing a graph that you collect data for and it just makes pretty much a nice straight line going up and to the right, this is a relationship we call directly proportional, meaning as you change the x value and it increases, the y value also increases with relation to it. As one goes up, the other one goes up. Okay, that means they're directly affecting each other. They make each other grow. Another relationship you'll often see with the data is what we call inversely proportional, meaning that it will make this type of U shape going down, and that means as x goes up, y is going to go down in relationship to it. Okay, as this one grows, the other one decreases. Okay, and again, inversely proportional meaning they do the opposite to each other. As one goes up, the other goes down. All right, and then the last one you'll see quite often is what we call proportional to the square, meaning that as one goes up, the other one goes up with the square of that value, meaning it increases more quickly than the other. Please avoid using the word an exponential. It's not an exponential graph. It looks like it. They both have kind of that U curve shape to them. But an exponential graph is actually much different than proportional to the square, and it's quite rare to see that relationship in physics. So you might have seen exponential a lot in math, but please don't use it in physics classes unless you're really sure that's an exponential graph. Often it's just a proportional to the square graph. Okay, so remember these types of graphs. We're going to see them quite a bit, and we want to be able to determine what type of relationship variables have with one another. Okay, the last thing I want to do is just do one example problem and make sure we got this graphing stuff down. So let's say we're doing an experiment where we're measuring the different positions of something at different times. Okay, now we won't worry about a title for this graph, but usually we want a title based on the specific experiment. But I want to focus on how we actually plot this information. Okay, so first of all, let's make our axes on our graph. So we're going to do some nice straight lines for our axes. Okay, and as I was saying before, if you ever have time as one of your labels, okay, then we need to always put it as the independent variable. So time is going to go down here, and it's measured in seconds. Okay, Position is going to go right here, and I'm going to try and write this sideways. We'll see how that goes. Not too bad, right? Because I can't turn my entire computer to write the word. Anyways, there we go. Position is measured in meters. Okay. And now we need to determine our axes labelings, our different spacings. So if we look at this and we say, okay, time goes between 0.5 and 3. Basically, we can say it goes from about 0 to 3. So we got a range of 3. We got quite a bit of squares. Okay. I'm going to think of these specific grid lines right here. We got 1, 2, 3, 4, 5 of those. Okay. So let's just make it easy on ourselves, and we'll make each one of these grid lines a second. Okay. These bolded grid lines. So this would be 1 second, 2 seconds, 3 seconds, 4 seconds. Okay. Again, it will make it a little bit smaller, but that's okay. We just want to make something that's easy to think about and easy to read. Okay, on position, we're going from about 0, 1.23, about 0 to about 45. Okay, so we have 1, 2, 3 of these big bolded grid lines. We could use the little ones if we needed, but we're going from about 0 to 45, so I think the easiest would be to go about to 15, 30, and 45. Okay, again, we can do it differently. It's okay if you choose a different set of that labeling, but just make it easy on yourself. Don't use too complex of labeling systems. Just make sure they're equally spaced and you should be good. All right, so now we just need to plot the points. So at 0.5, that's about here in time, and about 1.23 is just really low. I'm just going to keep it about right there. 1 is at 4.9, and this goes to about 15, so that's about a third of the way down or so, which is about right there. 1.2 is about here, and it's at 7, which is about halfway down this grid mark. Now we got 2.1, which is about here, and 21.6, which is about 6 away from 15, so it's about there. Again, I'm just approximating. It doesn't have to be super particular. And then 2.4 is about here. It's at 28.2, which is really close to 30. And then we got 3, and that's all the way up to almost 45, which is about here. Okay. So now hopefully you can see that we got this nice curve right here. So let's draw our best fit line, or in this case, best fit curve, which looks about like this. Again, not the greatest, but you can see that general trend going up there. And so last of all, for determining the type of relationship this is what we call proportional to the square. Okay? And there we go. Again, you wouldn't write it in the grid like this. It would be a separate part where you write the relationship. But that's our graph. We got our data, we got our equally spaced axes, and we got our best fit curve in this case, and what relationship it is. Okay, so I want you to get in the habit of always doing that for all the graphs in this class, and you'll be able to do that just fine, and you'll be able to see the trends that are occurring in our experiments. But that's it. Make sure to do the homework, and thank you for watching.